Hi everyone, I'm Ignacio and this is section 12. So in this first question they ask us to compute the derivative of the loss with respect to W1, and in this case we have that loss is equals to 1/2 of y minus y star squared, and then we have that y is equals to g of z, and then we have that z is equals to W1 x1 plus W2 x2. So we can compute this derivative of the loss just applying the chain rule, and then we have the derivative of the loss with respect to W1 is equal to the derivative of the loss with respect y times derivative of y with respect z times derivative of z with respect to W1. So then if we just derive the terms that we have below, we have the first derivative is the same as 2 over 2 times y minus y star, and then derivative of y with respect to z is just g prime of z, and then we have that the last derivative is just x1. So if we just substitute y equals to g of z, we end up having that this whole derivative is y minus y star, g of z minus y star times g prime of z times x1. So now in this second question, they ask us to write down the after rule when we want to minimize the loss. So in this case, the other rule, we'll change wy to be wy minus alpha times the derivative of the loss with respect to wy. So in the case of writing a send rule, have a plus here, but since we're now minimizing, the other rule is with a minus. In this third question, they ask us how the weights will change if we have the activation function that is 1 when z is positive and minus 1 when z is negative. So in this case, the activation function, if we draw it, it will be something like this, where here is 1, and then the lower part is minus 1. So we see that that whenever z is negative, the function is constant, and whenever z is positive, the function is constant again. So in this case, we have that g prime of z is equals to 0 all the time. What that means is that the whole derivative of the loss with respect to weights is of loss with respect to weights, that it was, as we computed before, g of z minus y star times g prime of z times xi. This will be equal to 0. Therefore, like, the weight won't change because our update rule is wy converts to wy minus alpha here of the loss with respect to y, right? So this term just vanishes because this term over here is 0, and therefore the weights remain unchanged. So as we said, in this case, g prime of z is equals to 0 always, and this means that we won't be able to learn anything because this will imply that our gradient will be always be 0. So there will be no learning at all. And this is the critical point of this gradient descent if we use this activation function. So this second problem is about decision trees. And the first question that they ask us is to write down the definition of entropy. So entropy for a random variable x is defined basically written down as h of x, and this is given by the sum of all the possible values that x can take, and then we have the quantity of having this value times the logarithm of 1 over the probability of having this value, where in this case x has values. This will be, I can write it xi, 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 and it will be x of 1 through xn. So in this second question, they ask us to draw the graph of entropy when x is a binary random variable. So in this case, we have that x can take values here -1 or 1, and the probability of x being equals to 1, let's say that this is equal to b, right? So in this case, the entropy, this will be, we follow the entire formula, with the probability of x being equals to 1, that it's p, times log of 1 over p, plus the probability of x being -1, and this will be, the probability will be 1 minus p, times log being 1 over 1 minus p. So if we draw this function for all the possible values of p, what we will get is a curve like this, where the maximum is 0.5 and it contains a value of 1. So in this third question, they ask us to compute the entropy of sport and then the entropy of position. In order to compute the entropy, we need to compute the probability distribution of sport on the training data and the same about position. So in this case, the random variable sport, I will denote it as S, that takes two values, either football, so we'll denote it as F, or basketball, right? And the probability of sport being equal to football, it's the ratio of the times that we have football in our training data set divided by the total amount of points, and this is 4 divided by 8, that is equal to 1/2. And then the probability of the sport being equal to basketball, we do the same. We have four examples of being basketball out of 8, and this is again 1/2. So we now compute the probability, the entropy of a sport, and this will be 1/2 times log of 1 divided by 1 over 2 plus 1/2 of log of 1 divided by 1 over 2, and this is equal to 1. Now we'll compute the entropy of position, and we'll denote the random variable as pos, and this can take the values either center, we'll denote as C, guard, or kicker, so we'll denote as K. And then the probability of position being equal to center, we have out of 8 examples, like 4 of them are center, so the probability is 4 over 8, which is the same as 1 over 2. And the probability of position being equal to guard is, this case is 2 over 8, this is the same as 1 over 4. And finally, the probability of position being equal to kicker is equals to 2 over 8 again, this is equal to 1 over 4. So now we can compute the entropy of position, and this will be 1 over 2 times log of 1 divided by 1 over 2 plus 1 over 4 times log 1 divided by 1 over 4 plus 1 over 4 again times log divided by 1 over 4. And this gives 3 divided by 2. So in this second part of the problem, we'll start dealing with decision trees. And the first question is about information gain. And we will, since the variable that we're interested on knowing is sport, we can put the information gain with respect a sport after we do the split on this variable. So Information gain we will denote as IG of random variable x given a split on a random variable y. How it's computed is the entropy of x minus the expected entropy after the split. So the expected entropy of the variable after we have a split with the variable y. So in this case, our variable x is equal to sport, and our variable y it's also equals to sport. So this corresponds to entropy before the split, and this is the expected entropy after the split. Right. So we have computed in the previous problem what's the entropy of the sport, and we have computed that it was equal to 1. So now we need to compute the expected entropy after we split on the variable sport. So if we split if this variable sport, we have two options: either sport is equal to football, and if sport is equal to football, then in that case the probability of sport being equal to football is equal to 1, and the probability of sport being equal to basketball is equal to 0, right? So the entropy of the variable sport after sport is equal to football is equal to 1 times log of 1 over 1, and this is equal to 0. Then in the other case, if the sport is equal to basketball, then we have that the probability of the sport being football is 0, and the probability of the sport being equal to basketball is equal to 1. So in that case, the entropy the entropy of sport given sport is equal to basketball, this is equals to 0. Then the information gain in this case of sport in sport is equals to 1 minus expected entropy. So how many times do we have football? In total, we have 4 out of 8 times the entropy of sport given sport equals football, and then plus 4 out of 8 that we have basketball of sport given sport equals to basketball. And this is 1 minus 4 over 8 and 0 plus 4 over 8 and 0, and this is equals to 1. Now we'll solve question number 2, that it says to compute the information gain when we do create different trees, one splitting with position, another splitting by name, and another splitting by college. So as we made before, in order to compute the information gain, we need to know the conditional probabilities of sport. In this case, given position, and then we'll do the same sport given name, and then sport given college. So in the first case, we'll go with position, and then let's consider that position is equal to center. So in that case, the probability of sport being equals to football given position is equals to center it's of one example out of 4, because for all the possible values that has position equals center, there is one that plays football, and there are 3 that out of 4 that plays basketball. So the quality of basketball, given that position is equals to center, this is 3 out of 4. So now we can do the same for all the other values. We'll have that position is equals to guard. We'll have that the probability of sport being football, given that the position is equals to guard. This is 1/2, because there are just 2 examples that have position equals guard, and one of them is football, and the other one is basketball. So we have position equals sport equals basketball, given that position is equals to guard. This is 1/2. And finally, what happens is position is equals to kicker. Then we'll have that the probability of the sport being football, given that the position is equals to kicker, this is 1, and the probability of having basketball is equals to 0. So now we're ready to compute the expected entropy. And how we do it is by accounting how many examples there are that has position equals center, how many examples have position equals guard, and how many examples have position equals kicker. So there is 4 out of 8 that has position equals center, and then if we use this condition, then we compute the entropy. If we know that position equals center, what we have is 1 out of 4 times the log of 1 divided by 4 plus 3/4 times the log of 1 divided by 3/4. And then we have that 2 out of 8 are position equals guard, and this has an entropy of 1/2 times log of 1 divided by 1/2 plus 1/2 times the log of 1 divided by 1/2. And finally, there are 2 more examples that has position equals kicker, and these are 2 out of 8, and the entropy of those are 1 times log of 1/1. And this gives a total of 0.66. So in this case, the information gain that we have of sport given position is equal to the entropy of the sport minus this expected entropy of sport given position, and this is equals to 1, as we have computed before, minus 0.66, and this results 0.34. So now we'll do the exact same thing, but with the variable name instead of the variable position. And for that, we have 6 possible names. One is Michael Jordan, and there's just 1 out of 8, and the probability of sport being football, given the name is Michael Jordan. The name is M, given the name is equals to Michael Jordan, then this is 0, and the probability of sport given equals to basketball, given the name is Michael Jordan, this is equals to 1. Then the probability name is Vince Carter, and we have 2 out of 8 of those, and one of them is playing basketball and the other one is playing football. So the probability of sport being football, given that the name is Vince Carter, it's 1 out of 2, and the probability of sport being equal to basketball, given that the name is hard, is equal to 1/2. Then for the following name, we have Maggie Bows, and there's just 1/8 of those. And then the probability of sport being football, given that the name is equals to Maxi Bows, this is 0. And then the probability of sport being basketball, in this case, it's equals to 1. So the following name is Tim Duncan, and we have 2 out of 8 of those names. And then the quality of sport in football, given the name is Tim Duncan. In this case, one of the Tim Duncans is playing basketball, and the other one is playing football, so we have that this is 1/2. And the quality of playing basketball, given the name is Tim Duncan, is 1/2 as well. So we do the same for Sebastian Janikowski, and in this case, there's just 1/8, and then the probability of playing football, in this case, it's 1, and then the probability of playing basketball, in this case, will be equal to 0. And finally, the last name is Langston Walker, and this also there's just 1/8 of this, and the probability of playing football is 1. So 1, and the probability of playing basketball then it's equals to 0. So in this case, we can just repeat the entropy, and we'll have 1 times log times 1 times log of 1/1. This is Michael Jordan. Then plus 2/8 of 1/2 times log of 1/1/2 plus 1/2 times log of 1/1/2. That this will correspond to Vince Carter, and then we can just keep adding all of those weighted by their respective frequencies, and this will end up being in an entropy of 0.5. And this corresponds to the entropy of the expected entropy of sport given the name. And then if we make some room, we'll, as we computed before, the information gain corresponds to the entropy of the variable sport except minus this expected entropy. So the information gain of the variable sport given name, this will be the entropy of sport minus the expected entropy of sport given name. Right? And this is we computed before it was 1, and then we just computed this value is 0.5. So the information gain in this case is 0.5. So now we'll do the exact same thing, but with the variable college. We have 5 different types of college. The first one is North Carolina, and we have 2 out of 8 of those. And in both people that are in North Carolina play basketball, so the probability of sport being football, given that the college it's North Carolina, this is equals to 0, and the probability of sport being basketball, given that the college is North Carolina is equals to 1. Then the following college is Wake Forest. And here we have 1 out of 8. And that person is playing basketball, so the quality of sport being football, given that college is equals to Wake Forest. This is 0, and the quality of sport being equals to basketball, given that college is equals to 1. The third college that we have is Oklahoma. Let's go, and we have 3 out of 8 of those. And one person is playing basketball, and the 2 other people are playing football. So in this case, the quality of sport in football given at the college, it's Oklahoma. This is 2 out of 3, and the quality of playing basketball, this is 1 over 3. Then the next one is Florida State, and then there is 1 over 8. And here we have the quality of the sport being football, given that college is equals to Florida State. This is 1, because a single person is playing football, so the quality of playing basketball, it will be 0. Finally, the last one is California. And here we have also just 1 person is in this college, and this person plays football, so the quality of sport being football, given that the college is California, this will be equal to 1, and the quality of playing basketball, it will be equal to 0. So now we're ready to compute the expected entropy of the variable sport given college, and this will be first the entropy of sport, given that we know that the person is playing in North Carolina, and is weighted by the number of times that we have people playing in North Carolina, so 2 out of 8, and this will be 1 times log of 1 plus the same for Wake Forest, it's 1 over 8, and this will be again just 1 log of 1, and then we'll do the same for Oklahoma, and this is 3 out of 8 times 2/3 of log of 1 over 2/3 plus 1/3 of log of 1 over 1/3 plus 1/8 of 1 log of 1 plus 1/8 of 1 log of 1. And this gives a total of 0.34. So now we can compute the information gain of the variable sport given college, and as we draw before, is the sport minus the expected entropy after the split, and this is given by 1 minus 0.34. This is equal to 1.66. Then the last question that they ask us is if do any of these perfectly classify the training data, and this is not the case because otherwise we'll get an information gain of 1 that is to perfectly know the data. And does it make sense to use name as a variable? In this case, it doesn't make sense because the variable name is completely independent of the sport that they are playing, so we will just be overfitting to the training data. So in this third question, they ask us how can we best cast continuous variables into discrete variables. And this is done by splitting the variable with a inequality relation. So we'll have that some attribute it's bigger than a certain value a, and this will be our splitting. And for instance, in this case, if we split the variable h into bigger or smaller than 34, we will perfectly classify the data. So now in this fourth question, they ask us to draw key decision trees that each correctly classify the training data and show how their predictions vary on the test set. In this case, as we said before, we note that if we split by the attribute h being bigger or smaller than 34, we can perfectly classify the data. So in this case, we have eight examples. 4 of those are basketball, and 4 of those are football. So if we classify by h being 34 as basketball, and h is smaller or equal to 34 as football, this will perfectly classify the data. And in this case, our first example in the test set will be classified as basketball, and the second one will be classified as football. And the algorithm that we are following is just the variable that maximizes the information gain. So in this case, the information gain of the variable sport given h is equal to 1. The final question of this problem asks us, what do we do when in the testing data we have a value that has never appeared in the training data set? So in this case, we see that example 2 has position being equal to defensive end. And we have never seen this value before. So what you do in such case is to put this case into the branch that has more numbers of items. So you put add this example to the branch that is more likely. And yeah, this implies to the branch that has more items. So now we'll do problem 3, that it's neural network representations, and we're given 8 different graphs, and we'll need to decide which of these graphs can the neural network represent. So in the first one, we see that the output of the neural network is it's just a linear transformation of our features x, and it has no bias at all. So yeah, then we have in this case our output has to be linear, and it has to go to the origin, like pass through the origin, or pass through the origin 0, 0. So if we take a look at all the graphs, the only graph that satisfies this relationship, it's A. So in this case, this neural network can just represent graph A. In this second question, we ask us what graphs can represent a neural network, where it has linear transformation, but in this case, we have a bias. So this just needs to satisfy one relation, that is like the function has to be linear. And in such case, we can represent again graph A. We're just adding, just putting B graph A with B equals 0, and the weight being equals to 2, and in this case it will be B equals to minus 5, and W equals to 4. So in this third question, they ask us what graphs can represent a network that has a linear transformation and then value. And as it's written in the problem statement, the value, it's the function that is given by max of 0 and x. So it cannot represent any negative values, so we have that value. It's always positive. So if we go at the graphs, we see that it has to be these were linear and just represent positive values, and the only one that satisfy the assumption is C and D. So in the case of Z, we have that W is equals to 2, and B is equals to minus 5. And on the other hand, we have on the graph D, we have that W is equals to minus 2, and B is equals to minus 5. And then with these values, the network would represent each of the graphs. In the fourth question of this one, they ask us what's the graphs you can represent in a network when you have two linear layers on top of each other. And in this case, the function it can just be linear because we have that so our output in this case it's W2 times the output of the first layer. In this case is W1 times X plus B1 plus the bias. So this is not just being W2, W1 times X plus W2 times B1 plus B2. So this we can just name this W and this B. So this is just being WX plus B. And we're in the same case than the question number 2. And therefore the only graphs they can represent is A and B. So in this case they ask us to determine the graphs that this network can represent when the first layer is a linear one, then it follows by a relative division, and then it follows by another linear layer. So in this case we have that these network can represent at least the same graphs at question number 3. Because if we set W2 to be 1 and B2 to be 0, then we have the same network as question number 3. So this implies that these can represent the graphs C and D. Furthermore, the linear can either translate or also scale the values, and it can also flip the sign. So this means that we can also represent graph E if we set the parameters W1 to be 1, B1 to be minus 2, and W2 to be minus 1, and B2 to be 1. So this is the last question, and they are asking us which graphs. These are network with 3 linear layers and and true values can represent. So applying the same trick as before, if we set the intermediate layer to be with the W2 to be equals to 1 and V2 equals to 0, then this layer over here is equal to the identity, which means that these two values is actually just one value. And this is the same network as question number 5, which implies that we can represent the graphs C, D, and E. So now if we look at the other possible graphs, we see that we can represent C, D, and E. And then we can just discard A and B because they don't have any flat regions, and we should have two flat regions since we have two values. So we can just discard these two. Finally, we can also discard G because this function is nonlinear since we have, although we have these values, and linear layers, our function should be piecewise linear. Then we can also discard H because it just has one flat region, and since we have two values, it should have two flat regions. And then we check that we can we can also represent F, so it has these two flat regions and is piecewise linear.